Okay, let's talk about standard deviation. First of all, I'm not going to worry about whether it's a sample or a population, and then here's the rule for rounding standard deviation. And this, what I'm using here is the electronic version of our textbook, which is also a different edition, so the page numbers are not correct. However, example numbers are the same. I believe this example starts on page 133 of our edition, edition or 5th edition. Okay. Standard deviation. Here's the deal. Standard deviation is basically a measurement of how much does the data vary from the mean. How much variety is that, or is it all clumped together? And the way we do that is we find, and this is not totally technical proper language, but it's sort of like the average of the distance from the mean for each individual data point. So basically, we figure out what the mean of the data is, okay? We subtract the mean from each data value. So, here's this paint sample that we did in class example. So we take 10 away from 35, and we get, in this case, negative 25, but right now, just don't worry about positives or negatives for the minute. And then we do the next one, 60, and we do the next one, 50, 30, minus 35, minus 35, minus 35, okay? And you're going to get a whole bunch of differences. And if we look at this in a table, which is a little easier, here's all our data values of the different paints, gallons of the brand A. Okay, and in this column is the difference between the actual data point, remember that's our X, mu is the mean, so it's the difference between the data and the mean. And now here's where the math comes in, and I'm going to skip this for now, but essentially what they're doing to square it is get rid of the positive negativeness going on, and they're just looking at just try to look at the numbers themselves and not the whole positive negative. So, but let's just pretend that these are all positive for right now. And essentially, we're going to add all these up if they were all positive and divide by 1, 2, 3, 4, 5, 6. And what that would do, in essence, it's not going to give us the exact right number, but what it'll do is give us a number that gives us the average distance from the mean that most of the data appears. All right, so having said that, let's compare the two examples that we're very familiar with, the Olympic age and our mountain data set. All right, remember from previous videos, we talked about how this bell curve is related to particularly the mode, that the highest peak is the mode. All right, and in the mountain data set we didn't have a mode. All right, so our mountain data set was not bell-shaped at all. All right, but back to the whole standard deviation. That's what these lines are. All right, let me scoot this down just a little bit here. Okay, this middle right here, that is our mean, and in the Olympic data set, our mean was 26. And we did our calculation, we got a standard deviation of 5. By the way, I'm rounding everything so the numbers are easy to work with. What that means is if we go out one distance, whatever that distance is, we can make that arbitrarily far, but we just call it 1, and we go positive 1 direction, 1 to the right, that means that this corresponds to the age of 31. If we go 1 standard deviation to the left, negative 1, this corresponds to an age of 21. Okay, 1 standard deviation to the right, we added 5 because that's what our standard deviation was. 1 standard deviation to the left, we subtracted 5 because that was the distance of our standard deviation. This was ages. Now I'm going to stop here for just a second and let's compare that to our mountain data set. Alright, we had an average, even though it wasn't the mode, just pretend with me that the average, our mean was approximately 5,000, Now see if you can do this and pause for a minute if you need to. See if you can agree with what I come up with here. So hit pause and see if you can figure out what would the height be at +1 standard deviation and -1 standard deviation. Remember, this was the height of the mountains in meters. So see if you can figure out the height +1 and the height -1. So pause. Okay, hopefully you paused. Here's the standard deviation, approximately 1600. So that means we would add 1600, and the height of a mountain that was 1 standard deviation would be 6,600 meters, and the height that would be -1 would be what, 3,400 meters, if I added that correctly. Okay, so -1 would be -1600. If we went 2 standard deviations, we would just add another 1600 and have 8,200 meters, and we would subtract another 1600 and we would have 1800 meters at a -2. Okay, so standard deviations, they're called deviations because what is the average deviation from your mean? How much does most of the data deviate, change from being in the middle? It's standardized because we can call it 1 and 1, +1 and -1, and +1 and -1, so that we can compare, incomparable data. I mean, what does Olympic ages have to do with mountains? Nothing, but we can talk about them in terms of a +1 and a -1 of a standard deviation. And here you go, big drum roll. This -1, +1 that I keep talking about, that is what we mean by a z-score. So when we talk about data having a z-score of -1 or +1 or 1.2, 1.3, all we are talking about is how many standard deviations are or is that data from the mean, from the middle. Okay, and a z-score of 0 means that it's right there in the middle. Okay, I'm going to stop this video here and talk about z-scores in more detail in a minute. By the way, I want to point something out very quickly before I quit. Notice that in all of this talk with the bell curve and the normal distribution, not once did I talk about quartiles, IQR. That's because they don't really go together. They do, but they don't. Okay, and trying to put this on top of the bell curve can get confusing. So I'm going to talk about this data completely separate. Mean, median, mode, and standard deviation all go together with this.